So the recorder has started, and today we are going to do an exercise on how to use HYSYS. Hopefully the screenshots will get saved. Hopefully the recording, whatever I'm speaking, will also get saved, and hopefully I don't have to repeat this tomorrow. Okay, so that is my hope. Alright, so go to the start menu. We have to find out where Hyprotech is. So let's see all programs. DC++ is very easily, I can find DC++, but I am not able to find Hyprotech. Hyprotech, HYSYS 3.2, HYSYS. Alright, so HYSYS has started, it will come online, and once it comes, then it will take a little bit. Did you confirm it runs here? Is that a yes or is it a no? No, HYSYS चलता है, इस पे confirm है? हाँ? नहीं चला तो फिर क्या बताएं यार? चलो. So go to the file menu, new case, and every case will have its set of components, right? So let us say you have a benzene, toluene, xylene mixture that is to be separated into whatever, pure benzene and pure toluene, xylene. Okay, so 3 component distillation. So I want to add what? Benzene. Yeah, so this is benzene. Let me just press enter. So benzene has been added. Toluene. So toluene has been selected. Press enter. That also has been added. Xylene. पैराxylene ही डाल लेते हैं क्यों? So we have selected whatever needs to be put in there, and I'm going to increase the size of the Spurti. Get the optical mouse. Every time this laptop is there, there should be an optical mouse attached to it. It doesn't matter. I want the damn optical mouse here. You don't think for me. You do what you're told. Okay. So we have added components. क्या हो गया? Now we'll add fluid packages. And the SRK or Peng-Robinson equation is a good, it's something that will do it for you. So let's see, which one do you want to add? SRK, just SRK is good. Okay. And once you've selected SRK, then you press. So number of components is 3. Number and the property package is Suave Redlich Kwong. This property package will be used to do thermodynamic calculations to figure out bubble point, bubble temperature, enthalpy of the liquid phase, vapor phase, etc., etc. All right. Now you press enter simulation. So you go into the simulation environment, and you will see this green, and there is this object palette which has got things like this is a material stream, this is a the red arrow is a what stream? Energy stream. Then you got pumps, heaters, exchangers, you got columns. Okay, so select a material stream. So I've got a material stream right there. This will be the feed. Select another material stream. I've got a material stream right there. Select another one. So this is the 1 is feed, 2 is distillate, 3 is bottoms. Then I need condenser duty. That's condenser duty right there. Then I need reboiler duty. That's reboiler duty right there. Okay. I also click and drag a column. This is a distillation column. Put it in there. Okay, so the column is in there. Okay. I'm going to do dynamic as steady state, and then we are going to do dynamic simulation together. Okay. So I'm going to also add some pumps and valves, okay, that are necessary. Why they are necessary? You use your own good sense to figure that out. Here's a pump. I add another stream here. Here's a pump for the distillate. I add another stream here. There's a pump for the bottoms, and I add another stream here, and I add energy for the pump. I add energy for the other pump. I add energy for this pump. Okay. Now we're going to make connections between the streams. All right. This is called the attach mode. So if you go to the attach mode, just a second. I think this has to be done using a mouse because you have to click and drag. Okay, so yeah, so if you go here, click, drag, and put it in there, connection is made. If you go here, click, attach. Blue to blue is a material stream connection. Okay. I also need some valves, so I'll go out of the attach mode. I'm going out of the attach mode. I want to put a valve there so that the flow to the column can be controlled. There's the valve. And if I go, well, I need to put some valves here too. Let me just organize the flow sheet a little better so that the streams are where they need to be and they're not, you know. Did you get it? What were you doing till now? I don't know, as you get older, maybe your patience goes down and down and down until you can handle it no more. Maybe that's how it is supposed to be. But my patience is running thin these days. बहुत जल्दी गुस्सा आ जाता है मुझे आजकल. If you know what I'm saying. Click, drag in there, put it in. So right now I'm just setting the structure of the flow sheet. How many valves, how many pumps, how many material streams, how many energy streams, etc, etc. Now I'll go to the attach mode and keep on making the connections. I go to the attach mode, attach this to this, attach this to this, this to this, attach this. Energy stream to this pump, energy stream to this pump, and finally energy stream to this pump. Okay, the flow sheet is complete. Let me just get out of the attach mode and decorate it a little bit so that it looks good and doesn't look so disorganized as it does right now. Okay, let's see. Just so that things look neat and I don't have to struggle. You go here, right click, transform, mirror about Y, and now you got it going that way. Alright, so this is your flow sheet. And what you have is the feed coming in, pumped through a valve into some tray in the column. Distillate, liquid distillate pumped out through a valve, and bottoms pumped through a valve. Alright. Now let's just start going from left to right. Let's just start specifying the feed, then we'll go to the column, then we'll adjust the operating conditions in the column so that we get the kind of separation that we want and build a base case for this column. Okay. So let's just say we've got, double click on that. Now you got to specify what kind of a stream you have. You'll have to specify C plus 2 things for this material stream to be fully specified. HYSYS does something. If something is fully specified, it will calculate everything. So for example, if you specify C plus 2 things, it will calculate the density, it will calculate the enthalpy, it will calculate everything, all the associated properties with that stream. Alright, the moment it can. So that's what we're going to do. So temperature, let's say it's coming from a tank which is at, I don't know what, 35 degrees Celsius. Pressure, the tank is slightly above atmospheric, so let's say it's at 202 atmospheres. Molar flow rate, well, 100 is fine, 100 kilomoles per hour. And then I go to the composition tab and then say, well, benzene is what, 33, everything is, let's say it's an equimolar feed mixture. Alright. Yeah, the amount of time it took for you to make the phone call is the amount of time it took for you to get the no? Well, if it's not recording, I can't stop, man. Okay, it's okay. Okay, 0.33, 0.33. I'd say 0.33. And if I say normalize, it will normalize everything to sum to 1. It will scale everything to sum to 1. If I say OK, you see this OK has come there. That means this stream is fully specified because I specified the temperature, pressure, the flow rate, as well as the composition. So everything is specified, so it did the calculations necessary, and now if you double click on this stream, you will see no properties. It's calculated everything. Molar density, mass density, volumetric flow, enthalpy, heat capacity, blah blah blah. Alright. So all the properties have been calculated. The fact that this string is dark blue, this stream is dark blue, implies that it is fully known. Now I'm going to pump it to a high pressure. So let's say I use a 2 kilowatt pump. 2 kilowatt. What's the pressure here? Pressure is only 503 kilopascal. So pressure has increased from 200 to 503 by using 2 kilowatt, a 2 kilowatt pump. You see, in order to be able to control flow, I need substantial pressure drop across the valve so that my valve is the controlling resistance that determines how much flow is flowing. If the resistance of the valve is very small, you can keep moving the valve, nothing will happen to the flow. Right? So the valve has to be the controlling resistance. If the valve has to be the controlling resistance, that means the pressure drop across the valve should be significant. So 500 to whatever, let's say this column is operating at 150 kilopascals, above, slightly above atmospheric. Okay, that's not a lot of pressure drop. I would prefer that this go to about 7, 8, 9 atmospheres. Okay, so I'll increase the, दो था इसको 3, 3.5 कर दो, 3 kilowatt. Okay, let's see what happens if you do it 3 kilowatt. You go here, the pressure is, ये क्या हुआ? I'm sorry, 3 kilowatt. I made 3 kilojoules per hour. 3 kilowatt. Now the pressure here is about 10 atmospheres, 9.5 atmospheres. Okay, so from 9.5 atmospheres to 1.5 atmospheres, that's a significant pressure drop. So when you move this valve, flow will change, right? Okay. This pressure, this is at the pressure of the column. The column, let us say, is, I don't know, maybe 150 kilopascal. Okay. Notice that once this stream got fully specified, I specified how much energy I'm putting in here. I got this stream. Then I specified what is this pressure. That sets the pressure drop. Alternatively, I could have also specified the pressure drop across the valve. And then this valve, this other stream number 9 would get fully calculated. Okay. The moment something is calculable, HYSYS will go ahead and calculate it. So you have to be very cautious what you are specifying. Okay. And keep track as to what you have been specifying. You see what I'm saying? Okay. Now let's double click on the column, go into the column. The condenser is a full, not a full, it's a total condenser. You got no vapor distillate. Everything is condensed. So the moment you pressed total, the vapor distillate stream went away. All right. Number of stages, I don't know, 25 maybe, 30? How many? 30. 30 stages. And by default, the feed is always coming in the middle. So let it be, the feed stage is 15th. Okay. That's it, huh? Okay. Go to the next tab, condenser pressure. Condenser pressure, let us say, is 140. And revolver pressure, let us say, is 160 kilopascal. Okay. A rule of thumb is per tray you will have about a kilopascal of pressure drop. That's a rule of thumb. We got 30 trays, I've got 20, well, slight, okay, let me just say that this is 170 because I've got 30 trays, huh? 170. About 1 kilopascal per tray. Okay. All right. Then I better have, yeah, I think it's fine. Then I go to the next, go next, be done. You see there is, the column is unconverged. There is this unconverged, कुछ दिख रहा है? The column is unconverged. In order to converge it, you need to specify two things so that the column can solve itself. You see, the feed is fully known, it's dark blue. Now the degree of freedom of this column is 2, right? It doesn't have a vapor distillate. So if it had a vapor distillate, the degree of freedom would have been 3. Since it doesn't have a vapor distillate, degree of freedom is 2. That means if you specify two things, HYSYS will try and solve for the steady state of this column, right? So I double click on the column. I double click on the column and I go to the, well, monitor is a good page to go to. If you go to the monitor, you'll see degrees of freedom 0, the active specifications are reflux ratio and distillate rate, right? Well, suppose these were not active, these two things were not active. You see the degrees of freedom is 2. If you see something saying degrees of freedom, that means there are there are 2 less active specifications. If I say active, degrees of freedom is 0, 1 or more specifications in the column are not fully specified, and then it goes. Well, distillate rate is one of the active specifications, reflux ratio is the other active specification, right? So it's asking what should the distillate rate be. I want pure benzene, right? So let's just say it's going to be 34, nearly 33.5. You see 33.3 kilomoles of benzene is coming in, plus a little bit of impurity, so I'm making it 33.5. Okay. Reflux ratio, I don't know, maybe 2. Okay. Aha. The column solved and it converged. Do you see this? I think today we'll just do steady state. We'll save it. Next class we'll take the same base case and do dynamics. Alright? I think let's just do it that way. We'll also figure out if the movie did get made or not. Alright? Okay, so the column is converged. Look at the temperature profile. The coldest place in the column is top of the column. The hottest place in the column is the reboiler. Okay? When you're looking at, okay, you see now these, all the condenser duty, you specified 2 things, distillate rate and reflux ratio. The condenser duty got calculated, the reboiler duty got calculated, the distillate and the bottoms and the distillate both got calculated, right? And if I specify this wattage to be, maybe I'll specify this to be what, 2, maybe 1 kilowatt, 1 kilowatt. How much does this give me? Yeah, it gives me sufficient pressure, about 9.5. And this, let us say, is going to another tank which is, I don't know, maybe at 200 kilopascal. Okay. Maybe I'll say this is 2 kilowatts. 2 kilowatts. How much did this pressure go to? 782. I think it's alright. Chalega. And let's say it's going to a tank. Where is the tank? The tank pressure is 200 kilopascal. Alright. So now you can see that your column has solved for itself. You can look at what the composition of the distillate is. Go to the composition tab and you'll say it's 99.4% benzene, about 0.5% toluene, no xylene. If you look at the bottoms, composition, very little benzene going down, 49, well, most of the toluene, you know, essentially a 50-50 mixture of toluene and xylene. Okay. Now, how do I know whether the operating conditions that I have chosen are okay or not? Okay, so I would like to operate the column at minimum reboiler duty. Okay, to do that, the column should give me a certain specification. One of the ways of specifying the specification is the following. You say, okay, how much of some material is coming in the feed, and what fraction of whatever is coming in the feed goes to the top, what fraction goes to the distillate, to the bottoms. Okay, this is called recovery. So for example, in this case, I will say recovery in the distillate of benzene should be equal to, I don't know, give me a number. 99%, 99.9%, what do you want it to be? 99.9. Okay, let's have a very clean separation. 99.9%. Okay. You see, I specified two things, reflux ratio and distillate rate. Alternatively, I can specify what should the recovery of benzene be in the distillate, and I could also specify the recovery of something else in the bottoms or in the distillate itself, some other recovery. So for the time being, I am saying recovery in the bottoms of toluene is equal to what? Just a sec. Okay, recovery of benzene in the bottoms is equal to what? Again 99.9. That's a pretty sharp separation. Okay, that's what we want. So what that essentially means is only 0.1% of the benzene that's coming from the feed is falling to the bottoms, and only 0.1% of the toluene that's coming in the feed is going to the top. That's what this specification means, right? Where recovery of a component I in the distillate, for example, is x of I in the distillate times the distillate flow rate. This is the amount of that component flowing in the distillate divided by z of I in the feed, right? So this is what fraction of whatever is coming in the feed is going in the top. Similarly, if you replace the numerator by xib times b, that is the recovery of that component in the bottoms, right? This is the definition of recovery. So instead of specifying the reflux rate and the reflux ratio, I would like to specify recovery of two components. In my case, this and that. Is that clear? Okay, so I'm going to rub it off. है ना, neat? This is pretty neat, man. यहीं कहीं समझा दो, यहीं कहीं मिटा दो. Sweet. All right, we get back to our, oh, just a second. ये यहाँ से ये मार्क क्यों नहीं जा रहा यार? Okay, for some reason it came. I must have clicked the wrong thing. Okay, if you double, what the hell happened here? If you go to the monitor page, the current possible specifications are reflux ratio, distillate rate, reflux rate, bottoms product rate. Right now I don't have any recovery as a possible specification. So what I say is I want to add a spec. What spec do you want? Column component recovery. I say add spec. Now it will ask me, just give it a decent name. What name do you want to give it? I'll call it D benzene. Distillate में कितना benzene? Okay. And then the draw will be what? What stream is the draw? Distillate. Then I'll have to, which stream am I talking about? I'm talking about distillate. So it's, I think, 2. Specified value, don't worry. Which component? Benzene. Right? I can specify a value, but right now I'm not specifying. Let's take a look at it. Let's take a look at, yeah, this is 2. So this is distillate. Okay, so if I go back to my, double click on the column, go back to monitor, you see I've got DBZ. The recovery in the distillate of benzene as a possible spec. I had another spec. Alright. What do I want here? Column component recovery. Huh? I say add spec. What component? It's in the bottom, toluene, right? So I would call it BTOL. Which stream are we talking about? We are talking about number 3, which is the bottom stream. Specified value I don't give right now, but the component that we are talking about is toluene. Alright, I've made all those selections. Right, now you can see these are 2 possible specs. If I say update inactive, right now whatever is the converged steady state, for that what is the value of this recovery and this recovery and all these other things, it will update. So I say update inactive. You see I'm having the amount of benzene in the distillate is 99.9% of what's coming in. However, about the amount of benzene in the toluene is only 99.4%, which is slightly lower than the 99.9% that I want. So what I say is, इसको कर दो ये inactive, इसको कर दो inactive. Okay, the moment you make these 2 inactive, it's at the same steady state, but now the active specs are these 2 recoveries. Now I say, well, I want this to be 99.9. Okay, it's converged again, and I would say that I want this also to be 99.9. Now if you do update inactive, you see the reflux ratio is slightly higher. The distillate rate is slightly lower. Earlier I had 33.35, now it is 33.34, right, and so on and so forth. Well, reflux ratio slightly higher means you are consuming more reboil. That makes sense. You want a clean separation, you need to put in more energy. All right. For example, let me just show this to you by adding another spec. Add spec column duty. Column duty add spec. Which stream? Energy stream 101. Niche wali. This is called reboiler duty. I'll call it QR. Okay, QR. And I just want to show you that. Okay, QR is another spec. Okay, update inactive. Just remember this number 4.872 E6. Let's just say I reduce this, or rather I reduce this. Let's just say I reduce both, man. 0.99, 0.99. And if I now do update inactive, 4.567. Amount of steam required in the reboiler is less. If I reduce this too, and I say update inactive, now it's only 4.2, and you can see the reflux ratio went down from 2.2 to 1.5 or 1.57. Do you see this or no? So what this is saying is, the cleaner the separation you want, the more the energy you have to put in, the higher the reflux ratio that you need. Does that make sense? Huh? All right. So what do you want, 99.9 or 99? 99.9 kar lete hain yaar. So we'll go back to that same steady state, 0.999. Went there, 0.999. This is my base case. Okay, this is my base case that gives me 99.9% recovery of benzene and toluene in the distillate and bottoms respectively. All right. Now I got this base case. As far as the operator is concerned, If I go to the monitor page, operator can adjust the reflux ratio set point. Operator can adjust the distillate rate or reflux rate or bottoms rate. Operator cannot directly adjust recovery. Is that clear or no? He adjusts the operating conditions. So operator typically would adjust the reflux ratio and the reboiler duty. You see what I'm saying? So the operator will adjust this and this, and then he will adjust this such that he gets the kind of recovery that he wants. Do you see what I'm saying? Now, so let us go to now I'm at the same steady state. It's just that as an operator I am specifying reflux ratio and reboiler duty. All right. Now let's just say I am maintaining the column reflux ratio at whatever 2.175, and I am maintaining the reboiler duty at whatever 4.8 blah blah blah. Okay. And I increase the feed to the column. Okay. So if I increase the feed to the column, instead of it being 100, let's say I increased it by 20% to 120. Column is still converged. Now let's just go to the monitor page and see. You see your recoveries have gone for a toss. The recovery of distillate in the benzene is 0.7654. That means only 76.5% of the benzene is going up the top, the rest is falling down the bottom. That makes sense. You are putting in more feed, your reboiler duty is the same, so you are not boiling up enough, so the benzene is falling down. Benzene which was supposed to go up is falling down. Does that make sense or no? So what do? You say, well, I'm going to apply a control system. See, right now the reflux and the reboil are not being adjusted. They are being maintained at the same value regardless of what is coming in. So for 100 kilomoles per hour, that reflux and or reboil is just fine. But for 120 kilomoles per hour, your distillate gets contaminated, right? Yes or no? So I say, well, I'm going to control some tray temperature in this column, and that tray temperature is going to be controlled by the reboiler duty. Okay. Now the first question is, which tray temperature should I control? One way of doing that is to look at the temperature profile, and if you go to the performance worksheet, column profiles, temperature, and I'll say, well, plots, view graph for the temperature, and you just blow it up. One way of selecting which temperature to control is to look at the temperature profile and find that tray where the rate of change of temperature is maximum. If the temperature is changing by a large amount from one tray to the next tray, that means a large amount of separation is happening on that tray, right? So if you hold that tray temperature constant, hopefully you are holding the separation constant. If not constant, almost constant. Do you see what I'm saying? So what I say to you is, this place looks like a good place to me. What tray number is this? This is 18. So let's say we are going to control 18th tray temperature. Alright? That's what we are going to do. So if I am controlling the 18th tray temperature, in terms of specs, what has happened? Operator is specifying the reflux ratio and the temperature set point for the 18th tray. The temperature controller will adjust the reboiler duty to whatever it has to give you that temperature, right? So now the specs are what? Reflux ratio and the temperature, but not the reboiler duty. Do you see what I'm saying? Yes or no? So I double click on the column. Oh man, I go to the design page, go to monitor, and I say add spec, and there must be some column column temperature. Okay, add spec, I'll call it T18 so that it tells me this is the temperature of the 18th stage. Huh? Which stage? I will choose stage number what? 18 कहाँ है? Okay, specified value, don't worry about it. Now I go back here, and if I go down, T18 is a spec. If I do update inactive, it's 119.1 degrees Celsius. Now instead of specifying the reboiler duty, I'll be specifying this, and I'm still at the same steady state. So earlier column operation was at a fixed reflux ratio and a fixed reboiler duty. Now I have column operation at a fixed reflux ratio and one of the tray temperatures being controlled, specifically the 18th tray temperature being controlled. Well, now I give the same disturbance, which is what? 100 going to 120. The feed rate going from 100 kilomoles per hour to 120 kilomoles per hour. ICS has solved itself, things have converged, and let's just go, I mean it's easiest to see it here. Update inactive. You see, there was no difference here. By controlling that one tray temperature, the reboiler duty has been adjusted appropriately so that your recoveries are maintained regardless of what feed is coming in. You see what I'm saying? Huh? Now let me add another possible disturbance is the feed composition changes. Feed rate can change, feed composition can also change. So let's just see what happens if I change the feed composition. Right now it's equimolar. Let's just say benzene goes down to 20% and the rest remains equimolar. So the rest remains what, 0.4 and 0.4? Normalize. Okay. Now the feed is higher, it didn't make a damn difference to the recoveries. Now I change the composition. Let me see if there was a difference, if there is a difference in the recoveries. Monitor. Aha. The benzene recovery in the distillate has gone down to 96%. That means a lot of the benzene that was supposed to go up is actually going down the bottoms. 4% of the benzene, instead of going up, is going down. Okay. What can I do for this? I would say control another temperature by adjusting the reflux ratio. Do you see what I'm saying? Here control, I can specify two things. Right now it's reflux ratio and tray 18 temperature. What if I remove reflux ratio as a specification and adjust some other tray temperature and control some other tray temperature by adjusting the reflux ratio? Okay. So to do that, again I'll have to go to the base case temperature profile. So again I'm going to go back to the same composition as before. 0.33, 0.33, 0.33, and I'm going to say, oh, kahan gaya yaar? Where did the mouse go? Normalize, and I say okay. Column has converged, and if I go to monitor and if I say update inactive, you know, I've gotten back to 99.9. Now I'm going to say, well, just a second, I also need to change the feed rate from 120 to 100 because that's my base case. Okay, now I look at the temperature profile, performance, plots, temperature, view the graph. I said I'm going to control what, 18th tray temperature right here, right? How about controlling the 15th, 14th, 13th? Okay, usually the feed temperature is never controlled even though the rate of change of temperature is large. This temperature change is there because the feed is cold. Okay. So this temperature change is because of the sensible heat effects of the feed. The other tray temperature changes are because of bubble point change. That means composition change. That means separation. So you should not control a tray, let's say 15, 14 and 16 cannot be controlled because they are too close to the feed tray. Other trays can be controlled. So let's say I'd say 13th or maybe even 14th. No, 13th, 12th. Okay. I'd say I'd control tray temperature 12. Okay. So I close this and I say, well, go to the design tab, go to the monitor page, and I say, well, add a spec. What's that spec going to be? That spec is going to be column temperature. Column temperature, add spec, and this is going to be T12, right? Stage, I have to choose the stage number. So I say, well, stage number 12. Specified value, don't worry about it. You've added the spec, and now if you look at it, T12 is empty. You can always say update inactive, and now you know what the temperature here is. It's about 101.5 degrees Celsius. Is that clear? Now what I'm saying is, based on this temperature, based on what the tray 12 temperature is, if tray 12 temperature is increasing, I'm going to increase the reflux. If tray 12 temperature is decreasing, I'm going to decrease the reflux. Reflux is cold. If temperature is increasing, more cold stuff you put in, temperature will decrease. If temperature is decreasing, less cold stuff you put in, temperature will increase back up. Alright. So this is no longer active. What is active is this. Do you see what I'm saying? So by playing with the specifications, I am actually having a control system. Each specification set corresponds to a certain operating policy. Where L by D and Q were my specs, operator was setting the reflux ratio and reboiler duty, how much steam you're putting in. When I put in L by D and T18, operator was setting the L by D specification and the T18 set point, and the reboiler duty was being adjusted by the controller. Now operator is setting the two temperature set points, T12 and T18. If T12 is not at set point, L by D is adjusted. If T18 is not at set point, QR is adjusted. Is that clear? Okay. Now let me see if I change the composition, does that affect my recoveries? That's the question. Earlier recovery went from 99.9% to about 96% in the distillate of benzene. Now let's see what's happening. 0.2 यही था ना 0.2 0.4 0.4 and then I say normalize, then I say okay, column has converged. I go to the monitor page and then I say update inactive. It fell slightly, but by not as much. Earlier it went from 99.9 to 96. Now it is going from 99.9 to about 99. Do you see what I'm saying? Yes or no? Now you may say that this going to 99.9 is acceptable, or it may not be acceptable. If it is not acceptable, then what do? Then you have no option but to take a composition measurement and adjust the temperature set point itself. Right now I have kept the temperature set point to be whatever it was at base case. By making no adjustments to the temperature set points and disturbance in the feed composition, I am getting a slight decrease in the somehow I am getting a slight decrease in the distillate benzene recovery. If this is unacceptable, then what has to be done is take a measurement of the benzene composition in the distillate and then adjust the top tray temperature set point, T12 temperature set point. Do you see what I'm saying? Yes or no? So I think this is enough for today. All right. What we have seen today is how to develop a base case of the simulation that you want, make different simulation runs, emulating different types of operating strategies. Yes or no? And what are those operating strategies that we talked about? I'm just going to draw it right here. Oh, sorry. I'll draw it right here. Maybe this is not the best way to do it. Maybe we need to do something else. Maybe this. What do you say? Maybe this is what we need to do. हुआ कि नहीं हुआ? अबे यार हटाओ ये सब. After 30 days ये एक्सपायर हो जाएगा. ओके फाइन. ओके सब कटाओ यार. Slowly but surely I'll get familiar with how to use it. So let's see. Let's have a black column and we'll have red controllers. How's that? अरे यार So this is your column with a feed coming in. All right. And now, oh, just a second यार. रुको यार रुको. एक यहाँ पे भी तो बनाना है. There is a way of saving it as a picture, you know. नहीं फाइल सेव नहीं यार, कुछ और है उसका. Just a second. I think since the movie is getting made, let's not play. धीरे धीरे कर करके आ जाएगा. Forget it. There's gonna be a valve here. There's a valve here. That's what I had missed. Okay. So this is your column. What you're doing is this is under flow control. And maybe the reactor level controller is setting the set point of this flow controller. Okay, so this flow is what it is. It could be 100, it could be 120, whatever. Then you've got a level controller. Then you've got a level controller right here. Okay. And earlier you have the first operating strategy that we did where we were specifying the reflux ratio was the operator giving the set point of how much steam you're putting in. So you're setting the reboiler duty. Of course, there's a pressure controller here. Okay, that's a pressure controller. I'm sorry, the handwriting has come out so bad, doesn't matter. And what you're essentially doing is taking this, sending it to a ratio controller. Based on what this is, multiply by the set point, that gives you how much reflux should be going in, right? So the operator is setting the set point of this guy and this guy. This is what we emulated by doing that steady state simulation, the first one, where should the feed rate change, should the composition change, if I keep my reflux ratio constant and my reboiler duty constant, what happens to my product recoveries? And we found that it went for a toss. Then what we did was, we put in a temperature controller that adjusted this. Set point. Okay? And we found that this guy can handle a throughput change, but if the composition of benzene in the feed stream goes down tremendously, the recovery of benzene in the distillate goes down by about 1%. Goes down by about 4%. 4%. Now 4% is unacceptable. Then we said, okay, can we improve it further? So the ratio controller has taken a lot of space. Maybe I'll use a different pen. Red, blue, green. हरा कर देते हैं यार, चलो ठीक है. Then what we did was, we put in another temperature controller. Right? And what did this temperature controller do? It adjusted this set point. Yes or no? And when I operated the column using this and maintained this temperature set point and this temperature set point at whatever its value at base case was, should the feed change, product recoveries are just fine. Should the feed composition change, distillate recovery, the benzene recovery in the distillate goes down by only 1% instead of 4%. So by adding this extra temperature controller, I am helping the benzene recovery in the distillate to improve. Now this 1% may or may not still be acceptable. Let us say it is unacceptable. Then what would you do? What you would do is take this, do you see what's going on here? So we have emulated all these structures in whatever we did. Does that make sense or no? Huh? So this is the base case column that we have developed. In the next assignment, we are going to control it using a single-ended temperature control and using dual-ended temperature control. We won't be putting in that composition cascade. Okay? So next class will be dynamics. So right now I just showed you, if you change the feed, where will the column end? Next time, what is the trajectory it takes to end up at those recoveries or those product compositions or whatever? How do the levels change? How does the reflux change? How does the reboiler duty change? Does it change smoothly? Does it oscillate, etc., etc.? These things we will see next time. Okay, so I think this is a good time to end the show, huh? And I really hope that it has been recorded, because if it's not been recorded, I have to do it again, and that will piss me off like anything. Okay, so I hope that will not happen. Recording stop कर दिया जाए क्यों?